Okay, it's 8:30, so let's go ahead and get started today. Good morning, everybody. How's everyone doing this week? Heard there's exams going on already, so for those of you who have exams this week, best of luck. So on that note, our exam is going to be next Wednesday. And so, I know people asked about kind of the format for the exams earlier this semester. And I was kind of playing with a couple ideas, but I think what ultimately what I'm going to do, just because, things are kind of so weird with the virtual thing, I'm going to have my exams be 24-hour exams. So what's going to happen is that next Wednesday at 8:30 a.m. I'm going to publish the exam. So it'll be given through Canvas's system. So you'll basically be able to view kind of question by question. And then you'll have 24 hours to complete the exam and then turn it in by 8:30 a.m. on next Thursday morning. So I think the way I'm going to do it is that I'm going to let's talk about the format for the exam for a second. So my exam usually there's two kind of big parts to it. So the first part is a short answer question, and so that's going to be problem one. Okay. And so these are very similar to the short answer questions that are at the beginning of every homework assignment. So basically, for these problems, I'm going to expect you to write maybe like 2, 3, 4 sentences, maybe write an equation or describe a situation, something like that. So if you're getting used to problem ones on the homeworks, these are going to be very similar to that. And so basically, the idea with these questions is to test your conceptual understanding of everything that we've been going over. And so usually this short answer question is I have this be worth 40% of the points. Okay. So it's a pretty big chunk. So, I think that concepts is something that's really important because, when you, are working professionally or you take another class, maybe next year or a few years down the line, I think it's really difficult to remember, the exact details of every equation that we went through. But the things that I want you guys to stick with is just the conceptual understanding of things. Like, what happens if you, submerge a surface into a body of water? What happens if you drop an object that's more dense than water? What's going to happen then? So, these concepts are things. I think these kind of form the basis of intuition, which I think ultimately will serve you much better than memorizing every detail of every equation. So that's why I put a lot of emphasis on these conceptual problems. Right, and so from then on, there's going to be 3 more problems. So problems 2, 3, and 4, and these guys will be problem solving. Okay. So in these problems, you're going to apply the formulas, just like we've been doing the homework to solve a situation. So I'll give you some kind of fluid mechanics situation, hydrostatic, manometry, stuff like that, and I'm going to ask you to solve for certain quantities. So these are again very similar to all the homework problems post homework problem 1. So you can kind of think of these as kind of the more traditional problems, and these will be worth just by process of elimination 60% of the points. Okay. And so even though we're having a 24-hour exam, I'll still design the exam as if it were like an in-class 75-minute exam, just because that's kind of the template that I have, and I don't really want to make a new template. And so you can basically, what I like to do for my exams is that once I write the exam, I always take it myself. First of all, just to find any typos, which happens a lot, as you guys know from the past homework, but also just to make sure that it's a reasonable exam. So usually what I like to do is I usually like to write a midterm exam, and I try to finish it within 15, 20 minutes. And I feel like, by that time, then you guys will have, 75 minutes will be enough for you guys to take the exam. So, at least, I know it's a 24-hour window, but at least reserve yourselves at least 75 minutes to do the exam. I would do more if you want. So, I mean, definitely take advantage of the full 24 hours if you need to, but also remember to sleep and eat and go to the bathroom and take care of yourself, right? Don't forget to do those things. And then, just make sure you submit on time. I think that's the main thing, right? Are there any questions on the exam format?
It's kind of just like the homework where we just submit a PDF.
Yeah, so Right. So I'm going to use actually the in tool or the Canvas quiz service. So I think what I'm going to do is I'm going to have each question kind of be its own thing, and you submit a PDF for just that problem. So you write out maybe your solution like problem 1 or problem 2. I think problem 1 I'll have you just type into the browser. I think that's kind of the easiest thing. And then problems 2, 3, and 4, I think I would just have the individual question, and then you would just upload a PDF for that problem. I think that makes it a bit easier for me to grade as well. Yeah. So the question in the chat is like, will there be a review session, and is this test just hydrostatic? So, so normally I do like to do a review session 1 week before the exam. We are quite a bit behind from where I want to be though. So I think you know I'm going to use that time to basically get us caught up a little bit. But you know, if people are interested in like a review session, I could probably you know, pre-record a video and upload something on that. Just because you know we are a bit behind, and I do want to make sure that we're caught up you know, with the lecture time. And this lecture time, I know this is the only time that, you know, I can expect you guys to be free all the time, you know, just because it's blocked off in your schedule. But for a review session, what I can do is I can pre-record a video. It might be, you know, probably the same length as a lecture, and then I'll upload that onto the Canvas site so that you guys can use that for review. So does that kind of sound good? Okay, great. Okay, so I'll work on that. And so the other thing I like to provide for exam prep is I always upload a study guide. And so basically the study guide will basically outline everything that you need to do. Oh, your first question, so or your second question. So the exam will also be covering Bernoulli. So the exam will be hydrostatics and Bernoulli. And so basically everything that's covered up until homework 3. So homework 3 is due next Monday. And so everything, homework 1, homework 2, homework 3, that's going to be the midterm exam. And then also just to help you guys study for the exam, I'll upload a study guide. The study guide is basically just going to be a collection of all the learning objectives that we covered so far. Don't go off the learning objectives that are actually in the notes, because you know I did skip some stuff, and so I'll probably try to upload the study guide by today, just so you can take a look at that and start studying that. So so look for the study guide. I'll give you guys a review session video probably by definitely before the end of this week, and then you know the exam's going to be, just write it out in writing. The exam's going to be Wednesday, 9:30. Okay, so a week from Wednesday. All right. Any more questions on the exam? All right. So the question is, are we still meeting in class that day? So I'll probably open up the Zoom session, but you know, the way I usually do questions for the exam is that usually I have you guys just send me an email. But if you want to pop into the Zoom session and send me a private message, just because you know I can't, you know, say everything kind of out loud, then I'll have that available for you. But you know, you're not going to be required to join in class that day, so you can just work on the exam just in your own place. Mm-hmm. Yeah. And also, you know, for those of you on Discord too, you know, in addition to emailing me questions, you can just private message me on Discord, and I'll probably and I can answer you there as well. That might be a little bit that might be easier to kind of exchange, because with an email, it's you kind of have to write a long thing, and then I write a long thing. So if you want to just ask a quick question, you can do that through Discord, and I'll make sure to answer that as well. Okay. So that's the details on the exam. So remember, that's going to be next Wednesday, September 30th. And so take a look out for the study guide. And then I'll post the review video by the end of the week. Okay. Okay. So the plan for today is we're going to finish up our notes on Bernoulli. And so basically, in terms of midterm content, today is kind of the last day. Wednesday we'll start something new, and next Monday we'll continue that new thing. But those new stuff, they're not going to be on the exam. So just, you know, the end of today's lecture, and we might finish early, and then I'll start the next thing. But just the lecture notes up to Bernoulli, that's what's going to be on the exam. Okay. Okay, so you know, up to this point, you know, we've covered Bernoulli equation, and we've covered, you know, the concept of, you know, how to use it and what it's about, and we've also covered the concept of stagnation and what that really means. And so today what I wanted to do was just go over just some more applications of Bernoulli, just so you can kind of see it in action in a lot of different examples. And just basically just do a bunch of examples with Bernoulli, just so you guys kind of get used to using it, okay? Right, so today's applications. Applications with Bernoulli, okay? Okay, and so let's go just do one example really quick. And I like to call this example kind of the leaky bucket example, because it kind of just looks like a leaky bucket, right? And so let's say that you have a tank of fluid. It can be water, it could be anything, right? And then at the bottom of the tank, we have a spigot, or you can think of it as, you know, someone stabbed your bucket of water. Okay? So we have water up here. We draw our triangle symbol. So remember that triangle symbol means that it's a free surface. Okay? Right. And so let's define the first point up here at point 1. And let's say that this height right here is h. And then we define point 2 to be at the spigot, okay? And so because we have a hole in this bucket, what's going to happen is that water is going to start leaking out, just like that, right? Right. And then let's kind of just write just a couple details. And so since points 1 and point 2 are both effectively kind of at the edge of the bucket, or not really inside the water, we can say that both points 1 and 2 are at atmospheric pressure. Okay. And so what we want to do is we want to solve for the velocity of the jet at point 2. Okay. And so the way that we can do this is with using Bernoulli. Okay. Oh, one more thing. So let's assume and so in these situations where you have kind of a very large tank like this, right? So obviously, you know, there's water coming out of the tank. But if this tank is wide enough, what we can assume is that the velocity at the top of the tank is basically going to be 0. Okay. And again, this is because the tank is very large. Right? And so, you know, the reason I say it's close to 0, because it's not exactly 0, right? Because if you have a leak in your bucket, you know, eventually the water level at the top is going to go down. But the rate at which the velocity of the water, you know, at the bottom of the tank, where, you know, you have this very fast jet coming out, compared to the velocity at the top, this is really fast and this is really, really slow. And so in these situations where you have kind of a very wide tank, we can basically assume that the velocity at the top is going to be effectively 0. So it's not going to be exactly 0, because the water level has to decrease because of conservation of mass, but it's close enough to 0 that in our calculations we can assume that to be 0. Okay? And so usually, you know, when these kinds of problems, I'll say explicitly in the problem that you can assume that the tank is very large. And so when I state that you know, you can assume the tank is very large, then any velocities at the top surface of the tank, you can effectively assume that to be 0. Okay. All right. Any questions on this, on the problem setup? Yes. Yeah. So h is from 1 to 2. Yeah. H is the height difference between 1 and 2. So the question is there a time when it's not 0? So, so yeah, so if you have kind of a skinny tank, like you know, you can think of it like a graduated cylinder, if you have a graduated cylinder that's very slender and you kind of poke a hole at the bottom, you have water leaking out, and then because the tank is so slender, is so slender, there's just not that much water in there. So as water's leaking out, then in order for it to maintain constant mass, then it has to basically go down like this. But if you have a really large tank, you can think of it as you just have like a ton of water in there. So you poke a tiny hole, and that tiny hole is not going to really make a big difference in the height of the water, just because the tank is really large. So so when I say really large, what I mean is really wide. That's kind of what I mean by that. Okay, so the way we're going to set up this problem is we're just going to apply Bernoulli between points 1 and point 2, and then we're going to see what terms cancel out and solve for U2. Okay, so let's write out our Bernoulli equation. So we have P1, P for pressure with a ponytail, over rho plus 1/2 U1 squared plus GZ1. Okay, and that's so that's all the Bernoulli quantities at point 1. So that's how we do this. And then next we have to write out the Bernoulli quantities at point 2. So at point 2 we have P with the ponytail, pressure P2, all over rho plus 1/2 U2 squared plus GZ2. Okay. And so remember, the Bernoulli equation is, as long as you can assume our 4 main assumptions, which is steady, incompressible, inviscid, and applied along the streamline, then what we can do is we can just say that all the Bernoulli quantities at one location have to be equal to the Bernoulli quantities at the second one, and then from here we can cancel out terms and we can solve. Okay, so let's start canceling out some terms. So remember our first assumption when we started this problem was that the pressures at point 1 and point 2, they're both exposed to atmospheric pressure. And so remember, usually when we have atmospheric pressures, we assume the pressure is going to be 0. Okay. All right, so that's the first assumption that we did. Next, let's cross out the velocity at point 1. Right? And this has to do with our large tank assumption. So because we assume the large tank, sure, I can repeat the last part. So the last part basically says that we cancel out the pressures in our Bernoulli equation because from our first assumption right here was that both points 1 and point 2, they're exposed to atmospheric pressure. And so if they're both exposed to atmospheric pressure, then we can cancel out the pressures and basically assume that they're 0. Okay, and so in a similar way, because we assume that our tank is very wide, our velocity at point 1 is also going to be 0, and so we can cancel out that guy as well. Okay, and so now that we've canceled out those terms, let's write out what's left. So on the left-hand side, we have G Z1 is equal to 1/2 U2 squared plus GZ2. Okay. Okay. And remember, what we're solving for in this problem is the velocity of the water jet at point 2, and so we want this guy. And so let's manipulate this equation to solve for that. So we have, let's subtract GZ2 from both sides. Okay, and so we have GZ1 Z2 minus Z2 is equal to 1/2 U2 squared. And so in this case, we know what Z1 minus Z2 is. So Z1 minus Z2 is just the height difference between points 1 and point 2. And so we know from the problem that that's h. Okay? And so if we substitute h in for that, multiply by 2, take the square root, and what we get is U2 is equal to square root of 2GH. Right? And so from our Bernoulli equation, we can see that if you have a leaky bucket, then you can find the velocity of the water that's coming out, and you just do 2 times gravity times the height of the from the top of the water to the leak. Okay. All right. Any questions on this, on how we applied Bernoulli?
So the initial velocity at 1, it's zeroed out because of the large tank at 0.1.
Exactly right. And so because our tank is really large, we assume that we know that the water level is going down, but it's going down so slowly that we can just effectively assume that it's zero.
Okay.
Yep. So the question is U velocity and Z is height? That's correct. Yeah. So U is velocity in this case. Yeah. I always do that kind of implicitly just because that's the standard, but fluid mechanics is a little bit weird because we use the letter U for velocity, which I think is different than like physics, and they use V. And so V makes more sense, but I think because in fluid mechanics we also have viscosity, which looks like that, then we use U to kind of differentiate between them. But whoever defined pressure didn't get the memo, because pressure and density rho look the same too. So it's symbols are weird. So the question is, so we cancel out pressure because both sides in the equation are atmospheric, or because pressure is zero at atmospheric. So it's actually both. So in this particular case, both pressures are at atmospheric, so you can cancel them out. But in other cases, what you'll see is that, points 1 and point 2, they might be at the exact same pressures. They might not be atmospheric pressure, but if they're the same, then they basically cancel each other out. So in this case, they're both of those situations apply.
So atmospheric pressure is technically 0 and not just 1 atmos?
So it is actually 1 atmosphere, but because atmosphere is kind of all around us, just for calculations, we assume that atmospheric pressure is 0.
Okay.
Okay. And so if you, speaking of physics classes, hopefully this equation might look a little bit familiar to you. And so, the situation that's kind of the same that you might have seen in your previous physics classes was something like this. And so if you take a ball and you just hold it out in your hand like this, or it could be any object, honestly, but if you take the ball and you drop it, right, and you want to find out what the speed of the ball is before it hits the ground, if you go back to your physics classes, you should see that it's 2gh, where h is the height difference in between these guys. Okay? And so it's kind of a cool connection between, probably something that you've learned before from physics and fluid mechanics, even though the equations are completely different, because they kind of follow the same principles of Newton's laws. That's why you get kind of this similar result. So kind of a fun kind of trivia thing, if you just to kind of connect the two things. Okay. And so that's kind of one example of how to apply Bernoulli. And so let's go to some more specialized situations. Okay, so let's talk about some confined flows. Okay? And so by confined flows, what I mean is that the flow is basically completely contained and that they can only go in one direction. Okay. And so some examples of this is, I think, flow in a pipe is kind of the most classical example of this. What the heck? Okay. And so some examples of flow in a pipe that you might see, in your household would be like flow through your faucet, all the pipes through the faucet, right? Or flow in a garden hose, something like that. Right? And so the key here is for confined flows is that there's really nowhere for the flow to go except in this prescribed direction. Right? And so these walls right here are completely solid, and so flow cannot penetrate through these. Right? And so flow is just kind of destined along one track. Okay? And so what's unique about these is that, because we have such a confined space for the flow to go through, we can, we can actually define, how much mass is in these systems. And so what's going to be important is going to be conservation of mass. And so this idea of conservation of mass is something that's actually going to be important for the next few weeks. And so, I'll introduce the concept today and kind of just give you a simple equation that you can use with Bernoulli, and then we'll expand upon this over the next few weeks. But conservation of mass is extremely important for fluid mechanics. Okay. All right, so another important thing to note for confined flows is that because the flow is completely confined, we're not going to be exposed to atmospheric pressure like we were in the last problem. So in these problems, it's very difficult to solve for like an absolute value of pressure because oftentimes you don't have a reference point to reference. And so in these situations, instead of asking you to solve for a pressure, unless I give you a pressure, what's kind of more common is that you're going to solve for pressure differences. Okay. And so like when you're applying Bernoulli, you're not going to solve for just P1 directly. What you're going to be solving for is kind of the quantity P1 minus P2. So you guys have already done this in the last homework. So the manometry problem, remember you solve for the pressure difference, PA minus PB. And so confined flows is kind of the same idea where you're not going to solve for the absolute pressure, but you're going to solve just for the pressure differences. Okay. All right, any questions on this? Okay. And so let me just kind of draw a typical example of a confined flow. So what I'm going to draw for you is a nozzle. Okay. And so let's say that we have flow coming into the nozzle on the left-hand side, right? And this velocity has a value of u1. Okay. Right. And so the other thing that we know about this nozzle is that the inlet area, or the area of the inlet face, has an area of A1, so that's going to be known. Okay. And so at the outlet face, we know the same quantity. So at the outlet, the area of the outlet face is going to be A2, and then the velocity there is going to be U2. Okay? And so for all the locations here, for both locations, we know both the velocity, and we also know the area. Okay? Okay? And so we're going to apply conservation of mass here. So if you kind of recall conservation of mass from your previous classes, what that means is that mass cannot be created or destroyed, right? At least not spontaneously. Right? And so the way that we apply this for fluids, remember fluids are kind of this constantly moving thing. And so the way that we can apply this for fluids is that, it's kind of a twist on the same thing where what we say for conservation of mass for fluids is that if you have a flow that's steady, what that means is that flow cannot accumulate or it cannot deplete in a certain amount of space, okay? Or mass. Okay. Right. And so if our flow is steady, then basically, we can't have any mass that accumulates or depletes. So another way that we can say this in kind of a form that's more useful for computations is that the mass flow rate into this area, in order for mass not to accumulate or deplete, this has to be perfectly equal to the mass flow rate out. And so, if you can compute the mass flow rate at one section of this nozzle, that has to be directly equal to the mass flow rate out of the nozzle. Okay? And so the way that we express mass flow rate in a moving fluid, so we usually give it the symbol m dot, right? And so the little m here denotes mass, and the dot above it kind of denotes rate, right? And so the way that we denote this is that we take the density of the fluid, we multiply it by the velocity, and we multiply it by the area, okay? And so this is mass flow rate. Okay. And then so if we apply this to this situation, and we can say that mass flow rate in, so let's compute mass flow rate in. Oh, sorry. I don't need ones right there. These are just generic. So mass flow rate in is going to be rho times the velocity at the inlet, which is U1, times the area at the inlet, which is A1. Okay. This has to be equal to the same quantity going out. And so you have rho U1 A1 is equal to rho U2 A2. And so this is how we express conservation of mass for some confined flows. All right. Any questions on this guy? Okay. And so let's take this one step further. And so if you notice in the last equation, the density is constant, and that's kind of part of our incompressible assumption. And so if we cancel out the density, what we get is actually something that's a little bit more useful, because you don't have to worry about density. And you have U1 A1 is equal to U2 A2. Okay. So this is just another form of conservation of mass when your density is constant, which for 95% of this class, we can assume that that's the case. Okay. And so now that we've canceled out the density from this guy, we have the product of U times A, which is the same as the product A times U, right? And so this guy is actually kind of a new kind of quantity that you'll see be used quite a lot. And this is what's called the volumetric flow rate. Okay. And this is often given the symbol Q. Okay. Right. And so the reason it's called the volumetric flow rate is let's write out the dimensions for this product. Okay. And so first we have area. So area has dimensions of L squared. Okay. Next we have velocity. We know velocity has the dimensions of length over time. Okay. And so if you multiply these guys, we have dimensions of L cubed over S, okay, over time. Again, I'm getting confused. Sorry. Okay, so we have L cubed over time, right? And so what we have is basically a volume over time. Okay? And so that's why we call this quantity volumetric flow rate, because it's basically the rate at which volume kind of travels in the fluid. Okay? And so you'll see me use this quantity Q or A times U. And so what I mean by that is just volumetric flow rate. Okay? All right, so the question is it the same as the one for thermodynamics? I haven't taught thermodynamics here, and it's been kind of a while for me. So I'll kind of cautiously say yes, but I'd have to kind of look at it and kind of see. But in this particular case, the Q doesn't have anything to do with heat. It has more to do with just the volume of the volume of fluid that kind of passes through over a certain period of time. Okay. So Q is not a unit. So Q is just the symbol that I give for volumetric flow rate. And so the unit, the typical units for volumetric flow rate, let's think SI units would be meters squared per second. Or if you want to look in English units, another common one would be inches cubed per second. Okay? And so these are the typical units for Q. And so if you see something with like some kind of volume measurement over time, then that's going to be a unit for Q. Okay. And so now that we have this concept of conservation of mass, we can combine that with Bernoulli to solve kind of some more interesting situations. Okay? So let's do an example of that, just to kind of show what that means. Okay. And so let's say that we have a compressed air. It's flowing through the hose and nozzle. Okay. Right. So looks something like this. So it comes in as a nozzle, just like that. Okay. So let's consider 3 locations here. So let's consider one location upstream, another location in the throat of the hose, and then one location here at the nozzle tip. Okay. And so basically in here we have our compressed air. Okay. And then because this is a tank of compressed air, we know the pressure upstream. And so let's say that we know the pressure at point 1 is 3 kilopascals. Okay. And then another assumption that we'll make is that at this part, I kind of drew it like this just to save space. But at point number 1, the tank is very, very wide. Okay. And so just like we did in our first example, because our tank is wide there, we can assume that the velocity is going to be 0. Right. And so we also know the diameter of the hose at in the throat, and so that's going to be 3 centimeters. Okay. Okay. And then we also know the diameter of the nozzle, and that's going to be 1 centimeter. Okay. Right. And so the last thing that we need, or the last information that we need to do this problem is the density of the air. And so we're going to use a density of 1.26 kilograms per meter cubed. Okay. Okay. And so we want to solve for 2 things. And so the first thing that we want to solve for is the flow rate of air. Right. Okay. And so usually in a problem when you see flow rate by itself, what that means is basically volumetric flow rate. Okay. And so the other thing that we're going to solve for is the pressure in the hose at location 2. Okay. And so in order to do this, we're going to use a combination of Bernoulli and also conservation of mass. Okay. Okay. And we also, and because it's kind of implicitly assumed in the problem that once the air leaves the nozzle at point 3, it's going to be at atmospheric pressure. Okay. So we're going to use that. We're going to use that tidbit to basically help us with Bernoulli. Okay. Any questions on the problem setup here? So let's go about solving it. Right. So let's do part A first. Okay. And so part A is asking us for the flow rate of air. And so remember, flow rate is given by Q, and it's going to be the area multiplied by the velocity. Okay. And so in this particular case, we have the diameters at least at 2 points in the at 2 locations in the hose. Okay? And so from diameter, we can kind of easily compute area. Okay? And so that that guy is good. Okay? And so what we need to solve for basically is we need to solve for the velocity at some location in the hose. Okay. And so the way that we're going to solve for velocity is we're going to use Bernoulli, right? Because Bernoulli has the velocity term in there, and so that's how we're basically going to solve for it. Okay. And so we basically have a choice right now. So you can either pick location 2 or location 3, right? And so let me write out basically the Bernoulli equation without any, or at least one side of it. Okay. And so on one side of the Bernoulli, remember that we have pressure, we have velocity, and we also have height. Okay. And so our height differences are going to be a wash in this case because everything is at the same height. You notice everything's horizontal. And so we're not going to worry about that. Okay. And then ideally, what we want to do is we want to set this equal to this exact same quantities at a different location, right? Okay. Where again, you know, we're going to cancel out the height because there's no difference in height in this case. Okay? And so basically to solve for the velocity in this case, we need to pick 2 locations where we either know the pressure, I mean, ideally knowing the pressure would be ideal, and we need to know the velocities at one of the locations. Okay? And so let's look at our 3 locations here in our problem, and let's kind of decide what we want to do. Okay? And so let's first look at location 1. And so location 1, we know that the pressure there is going to be 3 kilopascals. And so we do know the pressure. Okay. And then the fact that it's a wide tank means that we also know the velocity, and the velocity is going to be 0. Okay. And so since at location 1, we know both the pressure and the velocity, this is a great candidate to put into the Bernoulli because we basically have all the information here. Okay. And so let's make one of these guys location 1. And so we have P1 over rho plus 1/2 U1 squared. Okay. And so we know all of these. So that's good. And then our next candidate location will be one where we know the pressure because we want to solve for the velocity. Okay. And so first, let's look at location 2. So location 2, we know the diameter. It's going to be 3 centimeters. Right? But we don't know the pressure at 2. And actually, that's actually what we're going to solve for in part B. Okay. And so if we use location 2 for this part of the Bernoulli, we'll basically have 2 unknowns because we don't know the pressure and we don't know the velocity. Okay. And so let's say 0.2 for another time. Okay. And so finally, let's look at location 3. Okay. So location 3, we don't know the velocity because that's something that we want to solve for. But we do know the pressure. So the pressure at 0.3 is going to be atmospheric pressure. Okay? And we know that atmospheric pressure, most of the times we can cancel it out from our equation. Okay? And so let's use location 3 for this part of the problem. Okay? And since location 3 is at atmospheric pressure, we can go ahead and cancel out that guy. Okay? And then we can also cancel the velocity at location 1 because remember that's our wide tank. Okay. And so all that we're left with is pressure at 0.1, P with a ponytail 1 over rho is equal to 1/2 U3 squared. Okay. And so the only unknown in this situation is U3 because we know the pressure at 0.1, we know the density, we know what 1/2 is. So we can basically solve this for U3. Okay, any questions on just how I chose those locations and kind of just the thought process kind of behind that?
So why is it that we didn't go with point two again? Because we weren't given a pressure, so we had
Exactly.
two unknowns because of that reason.
Exactly.
Okay.
Right. Yeah. So location two, we're not given a pressure, and we got the hint because we need to solve for in part B, and so we'd end up with one equation and two unknowns that we wouldn't be able to solve for.
Okay.
Okay. And so now we have this equation. Let's solve for U3. And so if we manipulate the terms of that equation, we have U3 is equal to 2 times P1 divided by rho. Okay. And we solve for this. We get 69 meters per second squared, or meters per second. I swear that that's the number in the book, and I'm not 12 years old. Okay, so now that we know velocity, we can compute the flow rate, right? And so remember, the flow rate is just the product of area times velocity. Right? And so since this is the velocity at location 3, we need to multiply this by the area at location 3 also. Okay? And so the area at location 3 is going to be pi over 4 little d squared U3. Okay? And so we plug in all the numbers, and what we get is 0.00542 meters cubed per second. Okay. And so that's part A. And so part A, we basically, we use Bernoulli to solve for the velocities. And then once we have the velocity, then we multiply by the area, and that's how we got flow rate. Okay. Okay. And so part B is asking us to solve for the pressures at location 2. And so again, what we're going to solve is what we're going to use is Bernoulli. And so in this particular case, one of our locations has to be at location 2, but you can either choose location 1 or location 3, because at this point we know everything about location 1 and 3. Okay? And so just because I have it in my notes, I'm going to use location 1, but you can use whichever you want. Okay? I'm going to ignore the height, just because we know that the height differences are going to be 0. Okay. And so that's our Bernoulli equation between points 1 and 2, right? And so right away, let's cancel out this term, because remember, this is a wide tank. Okay. And so the velocity at location 1 is going to be effectively 0. Okay. Right. And so in order to solve for the pressure at point 2, we also need to know the velocity at point 2. Right? Oh. Yes. Okay, yeah, that's solved for. Okay. And so we don't know the velocity at location 2, right? But what we do know now from part A is the flow rate, right? And because flow rate has to be constant throughout the entire system, we can use this fact and conservation of mass to solve for the velocity at point 2. Okay. And so conservation of mass says that Q, which is our flow rate, has to be equal to, we know that it's equal to A3 times U3. Okay. And then through conservation of mass and the fact that this is a confined flow, this has to be equal to A2 U2. Okay. And so we can use this now to solve for U2. So we just divide both sides by A2, and then we can solve for U2. And so if we plug in, we can basically say that U2 is equal to A3 over A2 multiplied by U3. Okay. And we plug in the numbers, we get U2 is equal to 7.67 meters per second. Okay. And so now that we have that velocity, we can plug it back into our equation, and we can use that to solve for P2. All right, any questions on this?
For the Q equation, you have A2, but did you use D3?
Yes, I use D3. Yeah, little d.
Okay.
Yes.
So is it supposed to be A3 times U3?
Yeah,
Q?
it's yeah, A3. Sorry.
Okay.
Yeah, they have to be, yeah, the A and the U have to match at the same location. So if we're doing velocity at point 3, it also has to be the area at point 3 as well. Yeah.
Cool. Thank you.
Mm-hmm. Okay. And so we can plug all of that in. Right? We get P2 is equal to P1 minus 1/2 rho U2 squared. Okay. U2, which we just solved for. And we get that the pressure at point 2 is equal to 2,963 pascals. Okay.
That's a rho before the U2, right?
Yes. Yeah. So that's rho, density rho, because it has no no ponytail.
Okay.
Okay. Okay. So that example basically shows, you know, how you can combine both conservation of mass and Bernoulli to solve for these kinds of problems. Okay. All right. Any questions on that example? Okay. All right. So let's go over just some just kind of general concepts with Bernoulli. Just kind of take a step back for a second. Right? And so one thing that's very common for Bernoulli, the fact that, you know, if let's write out Bernoulli again, and let's ignore the heights again, right? Okay. And so basically this is our Bernoulli equation right here, right? And so the fact that, you know, we have pressure and velocity on basically the same side of the equation with the same sign, basically what we can assume here is that, or what we can see from this equation is that pressure and velocity are inversely related. Oh, yeah, I can definitely go back a page. Okay. Right? And by inversely related, what I mean by that is if pressure goes up, then velocity typically goes down. And then if velocity goes up, then pressure goes down. So it's like a seesaw between them. Okay? And so, you know, one way that you can kind of capitalize on this is that higher velocities are typically associated with lower pressures. Okay, and of course the vice versa is true too. Okay? And so one kind of application that you can use to kind of partially explain the flow is in aerodynamics actually. And so if you follow aerodynamics at any way, you're probably familiar with this shape. So this shape is basically an airfoil, right? And so the way that airfoils are designed, you know, air is going to flow around it. Okay. And so the way that these airfoils are designed is that the geometry of these airfoils makes it so that the air on top, the air that's flowing over the top of the airfoil, goes at a higher velocity than the air below it. Okay. So on top, basically, we have high velocity. And on the bottom, we have low velocity. Okay. And so if we go by the relationship that we have there, if we have higher velocity on the top, and we're basically going to have lower pressure, okay? And then lower velocity means we have higher pressure. Okay? Right. And so we basically have an imbalance here, right? So if we have higher pressures on the bottom, that means we're going to have higher pressure forces there on the bottom, right? And if we have lower pressures on the top, that means we have lower pressures on lower forces on top too. And so the net effect of this, and it's given just by the velocities, is that we have a net force upwards. Okay. And this phenomenon, where you have a net force upwards due to flowing fluid that's going over on the top and the bottom, this is known as lift. Okay. Right. And so I'll preface this by, you know, and I'll say that this is not the whole story of lift. So, you know, we'll get much more deeper into lift, you know, at the end of the semester. But just by using Bernoulli, which is, you know, basically our first equation for fluid dynamics, and just having this relationship between velocity and pressure, you can get this this kind of very elementary understanding of how lift works and how that's related to the velocities of the air that go over the top and the bottom. Okay? And so, you know, basically the upshot from this is that higher velocities, lower pressures, lower velocities, higher pressures, and you can manipulate the geometry and manipulate the flow in certain ways to get kind of behavior that you want, which in this case is lift for an airplane. Okay. All right, any questions on this? Okay. So that's one application for that, and so let's kind of just talk through another application. So you can actually observe this in your own home, right? And so let's say that you're taking a shower. Okay. 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 He has a surprised face because you know, we're peeking in at him showering, right? And so if you have a shower curtain, right? So a shower curtain is kind of a loose object, right? Use a different color for that. Okay. And so if you have a shower curtain that's kind of pretty loose and you're taking a shower, maybe sometimes you've noticed that the shower curtain actually gets pulled towards you, right? Like you're taking a shower and then the shower curtain kind of like starts hitting at your feet. So it's almost like a ghost is kind of like pulling the shower curtain towards you or pushing it towards you, right? But you know, it's not a ghost, and if it is, it's probably the ghost of Bernoulli. And so what's happening basically is that in this situation, you know, inside your shower, you have water that's coming down, and that's kind of also kind of pushing the air down too, right? And so inside the shower, what you have is basically a high velocity situation. Okay. Okay. And we know that if we have high velocity, then this means we have low pressures. Okay. But outside the shower curtain, you know, you basically just have still air. So still air has no velocity, or relatively low velocity. Right? And we know that for lower velocities, what we have is higher pressures. Okay. And so since we have this imbalance of pressure, you know, we have a higher pressure on the outside, what happens is that you have a force, a net force that's basically pushing on your shower curtain going this way, okay? And so when you have that net force, that's what basically creates the effect that the shower curtain kind of comes towards you like this. Okay? Right? And so because of this difference in velocities on each side of the shower curtain, you have this kind of net pressure difference, and that kind of pushes the shower curtain towards you. So that's what kind of causes that effect. So it's there's nothing wrong with your shower curtain, and it's not ghosts. It's basically this Bernoulli effect of the relationship between pressure and velocity. That's what the ghost wants you to think. Yeah. I won't comment there. Okay. Any questions on that?
Professor, where did you get the relationship about the inversely related?
Sure. So if we go back, so that comes just straight from our Bernoulli equation right here. And so our Bernoulli equation, the fact that we have both pressure and velocity on the same side of the equation, and they both have the same sign. And so basically, in order to always satisfy this relationship, say that we have P1 is greater than P2, right? And so in order to satisfy this relationship where they have to be equal, U1 has to be less than U2, right? Because we're forced into this relationship right here, where if one goes up, then the other one must go down in order to keep satisfying these things.
Okay, yes, thank you.
Mm-hmm. Yeah, so that's kind of one of the main consequences of the Bernoulli equation, is this kind of inverse relationship between pressure and velocity. Okay. So there's one more concept that I want to go over, and it's kind of another way to kind of cleverly use Bernoulli and conservation of mass, and this is this idea of measuring flow rate measurement. Okay. And so we've already seen that Bernoulli, we can apply it in lots of different situations, and if we combine that with conservation of mass, which is the product of density, area, and velocity, we can analyze a lot of different situations. But what some people found out, long ago, was that we can use this idea to basically measure flow within a pipe. Okay? Because in reality, measuring flow within a pipe is something that's pretty hard to do. So like if you think of like a solid, steel pipe, and you want to measure the flow through it, so like you turn on your hose or something, it's not like you can stick a ruler in there and you can measure the flow. It's something that's physically kind of difficult to do. And so the way that is that now we have a lot of very sophisticated devices to do so. But before the age of kind of digital technology, scientists and engineers had to think of a way to measure the flow rate in order so that they can design like aqueducts and all these kind of fluid mechanical devices. Okay. And so what they thought to do was that in order to measure flow rate, let's use Bernoulli for that. And so let me just draw kind of a simple situation here. And so let's say that we have a flow like this, where we have a wide upstream area. And so we'll call this location right here location 1. And we also have a location in the throat, and we'll call that location 2. Okay. And then let's say that we know the pressure difference between them. Okay. And the way that we know this pressure difference is that maybe we connected a manometer to this. So just like we saw in homework 2, where we had that differential manometer that can measure pressure difference. Okay. And so from that pressure difference, let's say that we want to solve for Q. Okay. Okay. And so basically, we're going to use Bernoulli and conservation of mass to come up with an equation that we can use for to solve for Q. Okay. And so before we start, let's first just kind of take a look at the situation. And so if we compare the two locations, we know that at location 1, we have a wide area, right? And so if we compare that to location 2, we have a relatively narrow area. Okay. And so by conservation of mass, we know that U1 is going to be less than U2, right? Because even though, because just by conservation of mass, we know that the product A1U1 has to equal to A2U2, okay? And so if A1, in this case, is greater than A2, in order to satisfy this relationship, we know that U1 has to be less than U2. Okay? And so, we just got done talking about the inverse relationship between velocity and pressure. That same inverse relationship also applies for area and velocity as well. Okay? And so if area goes up, velocity has to go down. Area goes down, velocity has to go up, because we always have to satisfy conservation of mass. Okay? And so the whole, a big theme of this Bernoulli chapter here is these kind of inverse relationships. So we have velocity and pressure, inversely related, velocity and area, also inversely related. So, that's kind of one good kind of, intuition to kind of take from this chapter. Okay? And so knowing that, let's apply Bernoulli, and then let's apply Bernoulli, and let's apply conservation of mass, and let's solve for the flow rate. Okay? All right, any questions on this? Okay. Okay, so let's apply Bernoulli between points 1 and point 2. Okay. Okay. And so again, I'm just because point 1 and point 2 are at the same height, I'm going to ignore the z term, but normally you would write the z term and cancel it out. Right? Okay. And so we have P with the ponytail 1, that's pressure at point 1 divided by density, plus 1/2 U1 squared is equal to P2 over rho plus 1/2 U2 squared. Okay. And so in this particular problem, we know what P1 minus P2 is, and so those are known. But we actually have two more unknowns here. So we don't know U1 and we don't know U2. And even though section 1 is wider, it's not quite wide enough in order for us to assume U1 is equal to 0. And so we're kind of a little bit stuck right here because we have only one equation, which is Bernoulli, but two unknowns. Okay? And so in order to alleviate this, let's use our conservation of mass. Okay. And so conservation of mass, we know that the flow rate, Q, is equal to A1, U1. It's also equal to A2, U2. Okay. And so let's solve for U1 and U2 in terms of Q. Okay. And so if we take basically just this first part of the relationship right here, and we divide both sides by A1, we get U1 is equal to Q over A1. Okay. And then if we take the second part of this relationship, we get that U2 is equal to Q over A2. Okay. And then what we can do from here is we can plug these guys in. And then we'll basically cut down our number of unknowns to 1 because we'll have everything in terms of Q. Okay? And we'll assume that we know the areas as well. Okay? Okay. Because usually it's pretty easy to just to measure the diameter of a pipe. You can actually do with a ruler. Okay. Right. Any questions on this?
Yeah, you mentioned that we were to the velocity. We're not ignoring it this time because it's not wide enough.
Right.
when it comes to a problem, will it be stated that it's wide enough to assume 0? Or
Yeah. So in problems, I'll basically say that, you know, if it's wide, I'll say that this tank is either very large or very wide. So look for the keyword very. Yeah. Okay. And so let's plug in for U1 and U2, and let's solve for Q. Okay. So we still have P1 over rho plus 1/2. And so if we plug in our expression for U1, we have Q over A1 squared. Okay. This is equal to P2 over rho plus 1/2 Q over A2 squared. Okay. And so now that we have this expression, we can solve for Q. Okay. And so let's put them all on the same side of the equation. So we have Q all over A2 squared minus Q over A1 squared. Okay. And this is equal to 2 over rho times P1 minus P2. Okay. And remember, in this particular problem, we know what P1 minus P2 is because of a manometer or something. Okay. And then we work on this, you know, a little bit more, and then we get the following expression for Q. Okay. So we get Q is equal to square root of this whole thing, 2 times P1 minus P2, okay, all divided by rho times 1 minus A2 over A1 squared. Okay. Right? And so what this equation states is that if you know the pressure difference in between 2 points, and you also know the areas, you can basically use that information to solve for the flow rate. Okay. All right, any questions on this?
Professor, does it tell us what direction of flow is, right?
Yeah. So it doesn't tell you. That's a great point. So Q right here is basically just a scalar quantity for the amount of volume that goes. But in order to get the direction, you kind of have to know that just from the problem itself. Yeah. Usually flow will go from higher pressures to low pressure. So that's how you kind of know what direction the flow is going to be.
Okay. Thank you.
Okay, so we have a couple minutes left, so let's do just a super quick example for this. Right. Basically just putting numbers on this guy. Right. So let's say that we have a flow in this exact situation. And so just a little bit of trivia. So this situation with the narrowing, this is known as a Venturi flow meter. Okay. Right. And so let's say that we have D1 is equal to 10 centimeters. And little d2 is equal to 5 centimeters. Okay. And then let's say our fluid here is water. And so water has a density of 1,000 kilograms per meter cubed. Okay. And let's say that the pressure difference, P1 minus P2, is equal to 5 pascals. And then we also want to solve, so we want to take these numbers and solve for the flow rate. Okay. And so we have all the information here. And so let's go ahead and plug it in. And so we have 2 times our pressure difference being 5 pascals. Okay. All divided by 1,000, which is our density, multiplied by 1 minus A2 over A1 squared. And so A2 over A1 squared, that's going to be pi over 4 D1 squared over pi over 4 D2 squared, right? Squared. Okay. And so if we cancel these guys out, then we have pi over 4 cancels out. We plug everything in, and we get 0.115 meters cubed per second. Okay. So just a very simple example, just so you can see it kind of plugged in like that. Right? Okay. Any final questions on Bernoulli? Okay, so that's all we got time for Bernoulli. So hopefully what you've seen here is Bernoulli is it's a very powerful tool, just because it's a relatively simple equation, and you just apply between two different points. But I want you guys to always remember the restrictions on applying Bernoulli. So remember that we have our 4 assumptions, right? So in order to apply Bernoulli, our flow has to be incompressible, it has to be inviscid, so there's no viscosity, it has to be steady, and also has to apply along a streamline. And so Bernoulli usually is kind of your first step for analyzing fluid dynamics, but it's important not to abuse it. So remember those four conditions on how to apply it. Okay. Okay. Yeah. So we have D1 over D2. That's that's right here. Okay. So that's all we got time for. So thank you everyone for tuning in. Oh, question?
Yeah. It's D1 over D2. How come it's not D2 over D1? Because on the
oh yes
on the setup it's area 2 over area 1.
Yes, thank you. I was kind of rushing a little bit. Yeah, so it'll be D2 over D1. All right, so the question is repeat 4. So 4 is you have to apply it along a streamline. Yeah. And so what that basically means that you have to follow the flow. So if your flow is going like this, then you can apply Bernoulli from here to here. But you can't apply Bernoulli from here. You can't apply Bernoulli from here to here because the flow doesn't go that way. So you basically have to follow the flow in order to apply Bernoulli. Okay, so we're a little bit over time. So thank you everyone for tuning in today. This recording will be up by later today. And remember, the midterm is just going to cover on today's topic. So thank you everybody. Have a great day, and I'll see you guys on Wednesday.
Thank you, Professor.
Yeah.
Thanks, Professor.
Thank you, guys. All right, are there any more questions on anything we covered today?
Yes, Professor. Sorry, just the Bernoulli equation, you said there were similarities to it to the work energy principle.
Mm-hmm.
That's similar to the conservation of energy, right?
Yeah. Yeah. So basically what that means is that you can think of, because in Bernoulli we have 3 terms, right? So we have pressure. Let me find a good page. Yeah, so we basically have, or I guess this is fine. So we have pressure, and we have velocity, and we have height, right? And so you can think of the velocity here as kind of a measure of energy, right? And so the faster a fluid's going, the more kinetic energy it has. So basically, the more energetic the flow is. And so the way that you get more velocity in a flow is, by work energy or conservation of energy, you have to perform some kind of work on the flow, right? And so work can come in two different forms for fluids. And so it can either come from pressure forces, so pressures will basically force your fluid forward, or it can come from gravity. So if your flow is going from a high place to a low place, then you can say that gravity is doing work on your flow. So by doing work, you're basically inputting energy into the flow, and by conservation of energy, that makes it have more kinetic energy and more just overall energy in general.
Okay.
Does that make a bit more sense?
Yes, yes. I was just trying to see the relationship, how you mentioned last time, of how, you know, you had your potential, you had your kinetic, and the other term is just pressure now, right? But so what would that be considered in terms like of, I don't know, I'm just trying to wrap myself like pressure.
Yeah. Pressure is definitely, it's definitely not, it doesn't have like a term like that, like kinetic or potential energy, but it's you can kind of think of it as just kind of work. And so kind of the most common place that you see kind of pressure energy doing work on a flow is actually in internal flow. So you have pipe flow going from, from like a reservoir to your faucet, right? So in order for it to get there, the pressure basically has to do work on the flow in order to basically get it over that place. So it's kind of like the same as if you took like a block and you kind of pushed it yourself, right? And so there's no real name for like kind of a manual force, so like pushing a block forward. But that's still considered work. So pressure is kind of that same thing where it doesn't belong to like kinetic energy or potential energy, but it can still do work because it's a force that's applied onto a fluid.
And pressure. Okay. I'm just trying to understand pressure a little bit more. That's like the big thing that I'm trying to wrap myself under.
Pressure is definitely one of the weird ones, and pressure is something that we'll see constantly throughout the class. So it takes a while, I think, to build up intuition for it. So definitely keep it in mind, and then as we go through the class, then hopefully kind of pressure is a bit more clear. But it's basically a force that can be done on a fluid, because a fluid's different from a solid, because a solid you can grab it and you can force it, but a fluid's kind of like weird on your hands, right? So you can't grab it and push it. And so the way that you kind of push a flow is with pressure. Yeah.
All right. Thank you, Professor.
Yep. All right. So Jenny, your question is for Bernoulli. You have assumptions: no viscosity, incompressible, and also it has to be steady. So nothing has to be changing with time, basically.